Hi everyone, welcome to another Doug's Lab video. In this video we'll be discussing the use and synthesis of carbon monoxide in the laboratory. Carbon monoxide has a formula of CO. It's a carbon triple bonded to an oxygen. Has a very, very low boiling point of minus 191.5 degrees Celsius. So it is a gas at room temperature and not easily liquefiable one at that. It's made in the laboratory using several different ways. You can react calcium carbonate with zinc powder and as an intimate mixture, which is strongly heated, and you end up with zinc oxide, calcium oxide, and our carbon monoxide. This method works, but it requires strong heating of highly basic oxides in the presence of glass, which tends to destroy glassware. So I don't prefer that method. The preferred method is to dehydrate formic acid using sulfuric acid. So you can see here that, well, we know that sulfuric acid likes to dehydrate things. In fact, it's such a strong dehydrating agent that it will steal the hydroxyl groups from cellulose to form water. So you can take things like sugar, mix it with sulfuric acid, you'll end up with just carbon and the water that the sulfuric acid has absorbed. So if you look at the structure of formic acid here, you can see there's a nice water that wants to break off. So the sulfuric acid strips the water from it and you're left with this part up here, which is carbon monoxide. So that's a very convenient wet chemistry method for making carbon monoxide and the preferred laboratory method. Before you begin synthesizing carbon monoxide, you should realize that it's a very dangerous gas. It's responsible for the deaths of thousands of people every year as a product of incomplete combustion in a confined space. The gas is odorless and will reach lethal concentrations very rapidly, especially with one of these syntheses here. So this is a carbon monoxide detector that you might find in a house. And on the back here it specifies that the carbon monoxide will trigger the alarm at 70 parts per million for 60 to 120 minutes, 150 parts per million, 10 to 50 minutes, and 400 parts per million it will alarm within 4 to 15 minutes. This is not really reflective of the lethal concentration. In fact, the lethal concentration can be lower than this because this alarm is designed to be plugged in a place where the carbon monoxide might be generated as an early warning to not enter that room. So, not for sleeping areas, is what it says on here, and I guess that's why. Carbon monoxide is not nearly as dangerous as something like hydrogen cyanide or phosgene or something like that, but it's still quite dangerous. I believe the threshold for lethality over a long period of time is like 35 parts per million, but there are various studies based on lethality, and of course it's person to person, so take that with a grain of salt. Carbon monoxide is used in industry very widely as a very useful organic building block. It's very reactive. It's a very reactive source of adding a carbonyl group to something. Carbon monoxide also has a very high affinity for many metals. There's a process called the Mond process that's used for refining nickel. Nickel forms an interesting compound called nickel tetracarbonyl, which basically is an adduct of 4 carbon monoxide molecules on a nickel atom. And so this carbonyl is a liquid at room temperature and atmospheric pressure, and it can be distilled from other metals which tend not to form carbonyls with carbon monoxide that are found in the same place as nickel. So it's an interesting way of refining nickel to a very high degree of purity. Carbon monoxide is also used in a process called hydroformylation, which is a very useful tool in industry used to make aldehydes, so making commercial aldehydes, benzaldehyde, things like that. Very, very useful. It's also used in the Fischer-Tropsch process, which converts carbon monoxide and hydrogen, or mixtures thereof. It runs them over catalysts at high pressure and temperature, and it can form long-chain hydrocarbons. In fact, this process is how most synthetic motor oils are made. So, as you can see, carbon monoxide is a very useful chemical to have in the laboratory, and it's very useful to be able to generate that in a safe manner. So, we'll now go about generating the carbon monoxide and show you some procedural details. So I've set up a demonstration carbon monoxide generator, which consists simply of a flask where you can place the concentrated formic and sulfuric acids and then heat them gently, which will evolve the carbon monoxide gas, and in this case the carbon monoxide will just escape this tube, whereupon I'll burn it at the end of this glass tube to show the flammable properties of carbon monoxide. However, in a laboratory setting you'd probably have some sort of gas drying train followed by an absorption unit for whatever you're using the carbon monoxide for, and then some scrubbers after that. This apparatus is designed to be explosion proof. Since carbon monoxide is flammable, it will explode in confined space when mixed with a sufficient amount of air. So the stopper is in place, and this apparatus is all put together loosely in the event that when I do ignite it at this tip, if the carbon monoxide in this tube and the whole apparatus happens to be at somewhere between the lower and upper explosive limits, I won't destroy my glass apparatus and spread acids everywhere. Instead, it'll just pop the core or this joint here. So to start the generator, it's pretty easy. All that needs to happen is to first place some 95% formic acid into the generator. I'm using 20 milliliters. This isn't really an exact science, but typically you use twice the volume of formic acid to sulfuric acid, and that efficiently facilitates the dehydration. And then now 10 milliliters of concentrated 93% sulfuric acid. And I must warn you, of course, that this immediately starts generating carbon monoxide, so this has to be done in a hood. This gas is immediately dangerous to life and health. And you can see immediately some gas bubbles form. I'll replace this joint. Sulfuric acid helps to seal the joint. I've already tested this apparatus with smoke by generating a large amount of smoke at the tip of this point, and I assured that all the smoke was escaping out of the fume hood. So I do know that any excess carbon monoxide that's being given off and just released into the room is actually leaving the fume hood and not endangering my health at the moment. You can see that mixing the two acids has immediately caused a reaction involving carbon monoxide. And this reaction is easily controlled by simply heating or cooling this flask with either an ice bath or a flame or something like that, and it's very easy to control that way. I'm now going to increase the speed of carbon monoxide generation by heating the bottom flask gently with a torch. The dehydration reaction itself is exothermic, but so much heat is lost in the generation of carbon monoxide that the reaction does not run away. It often requires external heating to go to completion. The carbon monoxide will now be ignited at the tip of the glass tube, where it burns with a pale blue flame. By heating the apparatus, we can increase the production of carbon monoxide and thus increase the size of the flame. As you can see, this is a very safe and controllable way to produce carbon monoxide. Burning the carbon monoxide in air forms carbon dioxide, which is harmless. And in fact, burning carbon monoxide is one of the most efficient ways to destroy it in the laboratory. So by feeding it into the air intake of a Bunsen burner or something, it's a good way to destroy it at the end of a reaction train. I'll be using carbon monoxide in several upcoming videos, but I decided that the procedural details for making carbon monoxide would be best left to a separate video, since it might clutter up a different video. So anyway, that is the production of carbon monoxide. I hope you enjoyed the video, I hope you learned something, and as always, please subscribe, like, and comment.